to look at a whole different way of solving constraint satisfaction problems called local search. So the idea is simple. We're going to maintain a complete assignment of a value to each variable, and we're going to start with a random assignment or some best guess to what we're going to do. And then we're going to repeatedly select the variable to change and select a new value for that variable. And we repeat this until we found a satisfying assignment. Okay, so what we're going to do is just going to try and iteratively improve our search algorithm. So the aim here is to find an assignment with zero unsatisfied constraints. And so given an assignment of value to each variable, a conflict is an unsatisfied constraint. So we're going to use the term a conflict as just an unsatisfied constraint. The goal is an assignment with zero conflicts, and we're going to try and minimize this function, which is the number of conflicts. So we're going to essentially do a search here with the number of conflicts. It's like the heuristic function in A* search. However, the path length doesn't make a lot of difference here. So the path length here is ignored. We're just really going to try to minimize the number of conflicts. All right, so here is a simple algorithm. So here's a simple version of this. So we're going to start with a random assignment. For each variable, we're going to select the value for that variable at random. And then we're going to repeatedly select the variable that participates in the most conflicts. So it might be more than one. We're going to select one of them at random. And then we're going to select a different value for that variable. I'm going to repeat this until we find a satisfying assignment. And here, all the selections are random and uniform. So we're going to assume that when we select the variable that participates in the most conflicts, we're going to select, if there are multiple of them, we're going to select it uniformly. So here's another variant of this, is that instead of predicting one that's in the most, we're going to select a variable at random that participates in any conflict. So the difference between this, let's go back here, is this part here. This is select a variable that participates in the most conflicts is the greedy, iteratively best improvement. And the any conflict is the select a value at random that participates in any conflict. They're the only difference between these two. So there's two sort of algorithms we can do. So let's try and, so which of the preceding algorithms work better? What would you guess would work better out of those two algorithms? And then the question goes, well, what does that mean? How would you tell if one is better than the other? So here's an example of where it might be. So here's a question. How could you compare the three algorithms when one solves the problem 30% of the time very quickly but doesn't halt for the other 70% of the cases? One solves 60% of the cases reasonably quickly but doesn't solve the rest. And one solves the problem in 100% of the cases but slowly. Which would you rather have? All right. So the summary statistics, such as the mean runtime, the median runtime, and the mode, don't make much sense here. So one could do the mean runtime, and if you do the mean, then these ones here have an infinite mean, because once you add in average in an infinity, it ends up being dominating. If you cut it off up some arbitrary time, the mean sort of just depends purely on how you cut it off. Okay. If we try the median, well, this one here is probably the best of these three, but only because of the 60%. If this was 49%, all of a sudden it wouldn't be the median. And there's no particular reason for preferring 40 over 60. Okay, so the mode runtime, well, the mode for most of these is infinite if they don't stop. So then you're always going to be biased towards very slow algorithms, even if they always stop. So one of the things we can do, we can compare them. And the other property they have is every time you run them, they produce a different runtime. So it's difficult to do it. So it's difficult to compare them. All right, so here's what we can do. One thing we do is this called runtime distribution. On the x-axis is the runtime, or the number of steps. And here we have it in a logarithmic form. And in y-axis is the proportion of the number of runs that are solved within this runtime. So if you look at these graphs here, the green graph here solves all of them, right? But in 10 steps, it's only solved 10% of them. In 100 steps, it solves 70% of them. The blue one here solves fewer of them. It only solves about 55% of them, But after 10 steps, it solves 30% of them. So if you're only interested in 10 steps, it's much better. The red one here solves fewer algorithms, but those that it solves, it does it much quicker. It does it in very few steps. So this is what we're going to do, is we're going to construct one of these. We're going to run the same algorithm on the same instance for a number of trials. So for example, 100 or 1,000. Remember, each time it's run has a different runtime. And we're going to sort the trials according to the runtime. And then we're going to plot on the x-axis the runtime of the trial, on the y-axis the index of the trial. And this is going to produce a cumulative distribution. And we're going to do this a few times to gauge the variability. So we're not going to talk about this, but take statistics is one of the is where you'll understand about how you're going to actually work out how variable these values are. It actually turns out not to be that variable. See, and sometimes we're going to use the number of steps instead of the runtime, because computers measure very small runtimes very inaccurately. However, using the number of steps is not a good measure to compare algorithms if the steps take different times. So we're going to work out whether we're going to use the number of steps or the runtime. In the examples that I'm going to show you, I'm just going to measure the number of steps. Okay. And then so another algorithm we could do is a probabilistic mix of greedy and any conflict. For example, 70% of the time pick the best variable, otherwise pick any variable in a conflict. Okay, so let's try and see what happens here. So what I'm going to do here is I'm going to look at this. So I'm going to run. So I have this program. So this is the CSPSLS. This is the Python code that's given for the next assignment. And we're going to look at example CSP2. Now CSP2 is this example. There are 5, there's A, B, C, D, E variables, and it's the same example that we used before. A is bigger than E, A equals D, B is not equal to 3, etc. Okay, so now I'm going to get a terminal, and I'm going to run this. I'm going to go. Okay, so I'm going to run this and pass the unit test, which is good. And here's what I'm going to do, is I'm going to do the greedy strategy here. So if we run this greedy one, this is the one that always chooses the best variable. So if I run this, it finds out here, it doesn't get an answer. If I run it again, it finds it in 20 steps. So sometimes it doesn't find an answer in 1,000 steps, but sometimes it does it in 20 steps. Every time we run it, has a different number here. It doesn't do it in 1,000 steps. Well, it's got 1,001 here because it also counts the initial random assignment. And it's found in 21 steps, and we do it again, it didn't find it in 36 steps. Okay, that's what happens with a greedy assignment. Sometimes it doesn't find it, and sometimes it does. And here's one that's sort of the any conflict. So this is one that just goes and finds any conflict. If we run this, we'll find out here it does it in 88 steps. Here it does it in 99 steps. And here it does it in 22 steps. So it finds the solution. We could do a probabilistic mix with this. So this says with a 0.7 chance, we can do greedy. Otherwise, we're going to do a conflict. So if we run this, we can find it in 21 steps or 45 steps, and 73 steps or 46 steps. So these are all random. Every time we try it, they get a different runtime in here. So now let's try and work out how to work out which is different. So what we're going to do is we're going to get a runtime distribution. I'm going to run this runtime distribution, and we run this, and it's going to have this as my plot. Doesn't make much sense now, but now I'm going to run the any conflict 1,000 times, and it's cut off after 1,000 times. So if I run this, it ends up with a distribution like this. So after 1,000 runs, after 100, at this point here, after about 100 steps, it solved a bit over half of them. Okay, so after 10 steps, it solved this many. Okay, and after the 10,000 steps, it solved nearly all of them. Okay, if I do the greedy one, so that's just looking at any conflict. If I do the greedy one, whoops, if I do the greedy one, it goes here. So this is just looking at 100% of the time I'm going to make the greedy choice. And we end up with this orange curve here. this doesn't solve all the problems, but some of the ones after 10 steps, it's sort of solved twice or 3 times as many. Okay, they cross here. All right, so that's what's happening here. So this is 1,000 runs, and here only just over half of them succeeded. Here most of them succeeded, but to solve the first 200, the orange was better. Now let's look at what happens with the mix of them. So if we run 70% of the time with the 0.7 chance, we're going to pick the best one, and with 0.3 chance, we're going to pick one at random. If we run this, we end up with this green one here, which turns out to be better than either one. Okay, it's still not as bad as this orange one, but it's much better than the blue one. So it turns out that a probabilistic mix of algorithms works much better can work much better than either one as well. Picking the best one tends to get stuck. Picking a random one doesn't work, but we'll need some way to mix those two up works well. So we could check how much, if you run it again, we could see what's going on here about how consistent these plots are. And here is the plot here. So this is the any conflict plot. So this is the blue and the pink are the same, and you see how with independent runs, with 1,000 runs, they have very similar distributions. So if we do the greedy, which is the repeat of the orange one before, and we wait for that to happen, and we find again that it's very consistent. So what happens here is it's very consistent between these values. And we'll try this same one again. Okay, again, this one here has a very, is actually doing much better. So again, probabilistic mix of these two things. Okay, so probabilistic mix of greedy in any conflict works better than either alone. And that's an interesting thing to know. All right. So what we're going to do is we're going to look at stochastic local search as a mix of greedy descent, which is going to pick the best variable and/or value, a random walk, which is picking variables and values at random, and a random restart is reassigning values to all variables. And some of these might be more complex than another, so a random walk might be pretty easy. And a probabilistic mix of these tends to work better than what we did before. Okay, let's stop now here.